Hi there, and welcome back to a new video that presents the new features available with Unreal 5.4 for PCG. For this episode, I want to revisit the first episodes where we're adding trees, rock, and grass into a more generic approach, while building up on what we have seen last episode about data assets. If you have not watched it, it might be good to do so. I will put the link on the top right. Today we will try to do something like this. It's a custom actor that is constrained by a closed spline and that spawns a hierarchy of meshes. It has trees, it has rocks, and it has grass. Splines are more interesting because we can shape the limit of our generation better. So if I change the size of my spline, for example, it regenerates automatically. As a reminder, you can set up yourself with the tutorial asset. The project is available on the GitHub. You will find the map and graphs, and all the previous episode data starting episode 5. I added instruction to set up it, either by downloading a zip or using Git. The link is in the description. Also, don't hesitate to join the Unreal Source community on Discord. We are starting to get a few people that are becoming more and more knowledgeable who can answer your questions. The link is also in the description. You notice that in the first episodes, we duplicated a lot of our logic for sampling, doing the same thing sequentially to build a hierarchy. If I go back to episode 5 and open the graph, first we spawn the trees, then we spawn the rocks, and finally the grass. What I want to present in this video is how we can leverage the new features of PCG to build this hierarchy in data assets, and have generic subgraph that will apply this hierarchy sequentially. Of course, it is important to have the info on the previous spawn to make sure we don't make meshes overlaps. That's why we have this difference node that took the point generated previously. It will be possible to do that with feedback loops in subgraphs. Let's dive right into it. We're going to start with a very simple case to illustrate how to work with splines. So I'll create a new blueprint class that I will name PCG Tuto Spline. In this blueprint, I'll add a spline component, and I will set up the spline a bit. So I already have a workable shape when we drop the actor in the world. Just adding a few points and make it a closed loop. Then I also want to add a PCG component. I can save and compile and drop that actor into the world. Then I create a new PCG graph that I will name PCG Tuto Sample on Spline and set it to my actor PCG component. So the first thing we want to do is to get a spline. So we're going to use get spline data. And since the spline is on the same actor than the PCG component, we can just get spline data on self. Then we want to sample some points in the interior. There is a new node in 5.4 that creates a surface from a closed loop, creates surface from spline. So this allows us to treat the closed spline as a surface, like the landscape. I can then plug it in the surface sampler, like we do with the landscape, and enable the debug. Make sure to generate it, and I have nothing. What's going on? As you can see, the surface sampler accepts a second input, a bounding shape. This limits generation to the shape provided by this pin. If no shape is provided, we take the one from our actor. In the case of the PCG volume, our bounding shape is the volume itself, and so the generation is constrained by the volume. But our actor only has a spline, so the shape we test against is the spline itself. If I debug my spline, you can see the small point sample along my spline, and the surface sampler will only keep points from the surface that intersect with those, because the default bounding shape here will be my spline. Since they are way too small, we have no point sample there. So in my case, I just want to change the surface sampler to unbounded, and now I have my points. Be careful with unbounded. If you try to sample on the landscape unbounded, it can generate a lot of points. But in this case, we want to sample the whole surface defined by the spline, so that's okay. From there, we don't want our meshes to float in the air, so we'll project the point on the landscape that will snap the points on it. So we're just going to add at the end a projection. And we want to project on the landscape, so we'll do a get landscape data and do the projection. If I debug this one now my points are snapped on the landscape. If I change the spline, I will have more points and all of them will be snapped to the landscape. So this is the best logic to generate points inside a spline. At that point, it is pretty much the same than sampling the landscape, like in previous videos. Alright, now we want to define our generation hierarchy. There are definitely multiple ways of doing that, but I will go with a setup that is similar to the one in the previous video. First thing I want is to define the meshes I want to use for a given hierarchy. I will need a custom structure for that, and we'll see why later. So I create a new structure and name it tuto mesh NID. The first member will be a mesh of type static mesh, and also an ID of type name. ID will indicate which item in the hierarchy the mesh is part of, and we'll see why we need it later. Then I create a new structure that will hold the one level of my generation. I will name it tuto mesh info. The first member will be of type tuto mesh ID that will define the pool of meshes for this level. I call it meshes, and it is an array. Then I can add another variable of type float that will be the density. Then I want to add some randomness in the scaling, so I will add a scale mean and scale max. We can also set the extent of our sampler for this level. Then we also have the ID. And potentially we can add a seed. Finally, we add a debug color of type linear color. It will be useful for identifying each hierarchy while debugging. For the default value, I'll set the density to 0.1, the scale to 1, the extent to 100, and we'll put a random number for the seed. Phew, that's a lot of info, and everything will be used in the graph. So from there, we want to create a new data asset. So it's a new blueprint class of type primary data asset. And since it's like a recipe, I will just call it tuto recipe. And it will contain one member of type tuto mesh info. I will call it mesh info and make it an array. And then I want to create a new data asset from the type we just created. So I'm going to create a new data asset of type tuto BCP. And I just call it forest. So I will add 3 levels. The first one will be trees. And the meshes, I will add a few meshes for that. Like a few trees from my assets. For all of them, I will need to set the ID. I'll keep a density of 0.1. I can change the scale to between 2 and 4. We'll change the extent to 30. You can just play with it if you want to. I put it to a random number, and the debug color for the trees will be green. Then I will do something similar for the rocks, adding a few meshes, changing the scale, making the extent a bit bigger. The ID will be the rock, changing the seed, and also setting the debug color to blue. And something for the grass. So here we have our hierarchy setup with different meshes and different level. The order is very important because we will spawn first the trees, then the rocks, then the grass. So let's go back to our graph here. I'm just going to add another data asset for tuto recipe, an object reference called data asset. It will be default by default. And then I can add another one that will be a boolean for just debug. So I'll remove the sampling and the projection. We're going to do it in the graph. And so the first thing I want now is to get the data from my data assets. If you watch the previous video, you know the drill. I get the path to my parameter and plug it into a get property from object path. And I want to extract the property mesh info. So if I inspect it, you can see that I have 3 entries with the density, the scale, the extents, the ID, the seed, the debug color. But we are missing our meshes. That's because we hit the limitation of the get property for object path. We can't extract struct that has an array, and at least not while extracting the whole struct. But you can target an array in a struct. So we're just going to create another get property from object path. And this time we're going to extract exactly what we want, which is mesh info, and inside it we want to do meshes. So I'm going to do mesh info, that meshes. It manages to get the array with the meshes and the ID. But as you can see, it was an array of array, so it's flattened in our attribute set. That's why I added the ID to the mesh. We needed to only select the meshes that will match with the ID of the level we are trying to generate. So the rest of the logic is to loop on each element of our initial array and apply some graph logic to it. To loop in PCG, we need to create a subgraph and specify the pins that will be looping. And the pin that will loop with the number of data plugged into it. The number of data is not the index here, it is the number of items you have in this list. We want to iterate on our parameters, but at the moment, we just have a single data with 3 entries. We want to partition it into 3 attribute sets. Each will contain just a single entry, one for each level. To do so, we can use the attribute partition node, and we want to partition on the index. If I inspect the result, you can see that I have now 3 attribute sets in my data collection, and in each, there is only a single entry. Now we can create our loop subgraph, and I call it PCG tuto recipe spawning. Let's set up the input pins. We can discard the default one, and we create the first one that will be our surface. So I will call it surface. Its usage is normal because we'll use the same surface for each iteration. The type of a pin is surface, and I'll mark it required so that our subgraph won't execute if there is no data provided on this pin. The next one will be our parameters, so we'll name it params. It will be of type attribute set, and this one is a loop. We want to loop on all our params. We also want it to be required because it doesn't make sense to not provide it. Then I'll add a third one that will be our meshes. In this case, it's just a normal pin of type attribute set, and we also put it required. And we'll have a final pin that will be our feedback pin. It will contain nothing in the first iteration, but for the following one, it will contain all the points that were generated before. Since we'll use an union for previous points, I'll set the type to spatial. We'll name it previous point and mark it as a feedback loop. In a nutshell, we'll loop on each data that will be provided on the param pins, and we will receive each time the previously generated points. For our output, I changed the default output pin type to point and mark it normal. It will output all the sample points. And I also add another pin for our feedback. And it's important that the pin is the same as the input one, so I name it the same, previous point, set the usage to feedback, and make it spatial. At every iteration, we'll output the previous point in this pin, and it will feed back as an input in the next iteration. And because we wanted to have some kind of debug, I will just add a debug flag. So I can go back to my original graph, and I can drag and drop the PCG graph into my graph, and then I can just create a loop node from it. I'm going to plug the surface. I'm going to plug my params, going to plug my meshes, and I plug nothing into previous points because it will be just generated inside this loop. Coming back to my loop graph, if you inspect the debug info, you can see that now I have the PCG tuto recipe, the loop, and I have 3 iterations in it. I can go to my input, inspect it, and go to 0, and you can see that I have my surface, I have my param that are the trees, I have the meshes that are all my meshes, and I have the previous points that have nothing. Now that everything is plugged and working, I will just forward our debug flag. So I will just get debug and plug it into our subgraph. Another addition in 5.4 is that you can see now that the edges are fat when they have multiple data. So when you have multiple data here, you can see that the edges is fat. All right, all is set up. Now let's implement the loop logic. We can go back into your subgraph. First thing, we want to make sure that for the params that is going to give us the current ID, we want to gather the meshes that correspond to my idea. To do so, we're just going to use, for the meshes, an attribute filter. What we want to filter, if we want to filter the ID, so we're going to target attribute will be the ID. We want to filter this one, and we want to make it equal. We don't want to use a constant threshold. We want to use the threshold that is coming from our params, and we want to use the threshold attribute to be ID. Basically, what we want to do is we want to make sure that for all the inputs in the meshes here, we want to use the attribute that is passed as a param of type ID here to get only the one that has exactly the same one. And so if I go outside, at the end, you can see that inside the filter, I have all my trees. And outside the filter, I have the rest that I don't want to use. And so if I go to my next iteration with the rock, you can see that inside my filter, I have the rock. And outside my filter, I have the tree and the grass. And same thing for the grass. Inside we have the grass. And outside we have the trees and rocks. So now that I have my meshes, I want to extract the parameters that are inside my params to impact the generation. So I'm just going to extract all of them. To extract all of them, I'm going to use the filter attribute by name, which is going to be called delete attributes, but I want to keep only selected attribute. And I want to keep the density. And I will do the same for all my parameters. And I can verify I have just what I need in all of them. All right, now I'm set up to do actual work. All my parameters are ready, and I have my array of meshes to spawn here. So we add back the surface sampler, and we're going to use the surface from it. I'm just going to move my parameters out of the way. In the surface sampler, we want to override the point extent by the value that is coming from our params, and same thing for the seed. And we want to use the density for our points per square meter. So I'm just going to reorganize my graph for that. Now we can debug the surface sampler, but not without setting it back to unbounded, like in an example graph. And I have all my points. The ones that are generated with the first iteration, the one that are generated with the second, and the third. So we have the big box that are the rocks, the small box that are the trees, and the very small box that are the grass. But it's a bit difficult to know which one are those. So to help us with that, we're going to add a way to debug them. But we don't want to do it when we don't need to. So we're going to use a branch node. This will allow us to output it to A or to B and get the generation of the other branch. Our condition will be get debug. And so if I plug the surface sampler into the branch, and debug is false by default, it will output to A. And you can also see that output B pin is grayed out, so it means it's disabled. So for our debug branch, we're going to add a copy attribute. It looks like it is disabled. That's because the branch is cut for now. And we're going to copy the debug color into our column. So our input source will be the last attribute, and our output target will be the color. So if I go there on my actor and I say OK for debug, and I select my elements, you can see that now my points have the color set. And then what I want to do now is to use the debug node. And we'll do the same thing as we did in the second short episode. That is to change the material override to PCG debug material color. If you don't see it, make sure that you have show plugin content that is enabled here. And so now we can clearly see our different points. We have the tree in green, the rock in blue, and the grass in red. And if I remove the debug, it just disappears. So now we know that the sampling is working. So we'll do as usual to add some randomness is to add a transform points node. We'll have a random rotation on Z. And for the scale, we want to use our params. So I'm just going to override scale min by our scale min param, and same thing for scale max. And to verify that it's working, we can plug this one into our debug branch. Re-enable the debug. And voila. Now we can assign our meshes, so we'll do the same thing as we did in the previous episode, which is the match and set attributes. Going to plug our meshes coming from our attribute filter. It will select random items from the list, and then we can verify that in our set of points we have different meshes. And we can then plug it into a static mesh spawner to spawn our meshes. We use mesh selectable attribute, want to do mesh, we just name of attribute. And it's working pretty well. I just disable the debug. There you have it, but it's floating. What I'm missing? I'm missing a projection somewhere. So after the sampling on the surface sampler, I'm just going to add a projection node to project the points onto the landscape. So we have our meshes, but they are overlapping with each other. That's because we didn't do any difference between the points. We want to make sure that our points generated on an upper level hierarchy will remove the point of the current level. So on the output node, I'm going to output the point that were generated. But I will also want to provide the point generated to the next iteration. So we're going to do a union node from our current level points and the points coming from the previous iteration. But having this big edge across the graph is not pretty. So we're going to use a new feature coming from 5.4, which is the named reroute. So I can add a new named reroute. This will add a new node in my list, which is the named reroute that I just created. I plug it into my union and then plug the result into the feedback bin. So now, if I go back to my input, if I inspect it for the first element, previous points you have nothing. On the second iteration, you have like it is 58 points, and on this another one, you have 104. And so what we want to do is after the transform, here we want to add a difference. We want to do it binary and discrete. And if you remember correctly, we had to be careful with difference with points because the steepness of the point can influence the difference. So before we had to do some operations to set the steepness, but now it's directly available on the sampler and you can just set the point steepness to 1. And I want to do the difference between my sample point and the previous point. And I can reuse my named reroute. So we're going to collapse our difference and use it for our debug branch and also for our match and set. And that's better like this. So we still have overlaps. That's probably because the rocks extent are not big enough. Let's debug to see exactly what's going on. So the trees are perhaps a bit too big. It seems okay for the grass, but it's not enough for the rocks. We're just going to change them. So we can go back to the forest and change, perhaps make extents for the grass a bit bigger. So we'll go to 10. I'll make the rock one a bit bigger. Yeah, that's a bit better. It's not perfect. Can do better, probably, but it's good enough for this tutorial. And so, pretty much done. If I change the spline shape, it will regenerate. And with that, we reached the end of what I wanted to show you today. It was a packed video with a lot of information, very dense, so take the time to digest it. Using Subgraph makes the system very powerful, but also makes it a bit more complicated to understand what is going on. So it is important to understand how you can debug it using the inspection or debug colors. Of course, I use Spline for this tutorial, which also applies to a PCG volume, or you can replace the projection on the landscape by the Wolverine query node if you need to project on static meshes instead, like we did in the short episode 1. That's all for today. I hope this sparked some new ideas you can implement in PCG. I'll see you in the next one. In the meantime, have fun with the plugin. Take care.